So here with us is Edwin, Delta Charlie 9 Oscar Echo, and he's a radio amateur. He's licensed since 1969, so quite a long time. And he has a background in electronics, and he's worked on high frequency equipment from the beginning of his professional career back in the 1970s. To focus on the development of hardware and software for software-defined radio systems. And this has resulted in modules and even a complete team, the web shop of the Charlie 25 Club. And his team has now started to explore higher frequencies, meaning anything from 4 meters to 13 centimeters, at least, and of course, including the popular downlink for the QR100 Oscar satellites. And this is why he's interested in higher order Nyquist zones. And now we're playing the pre-recorded talk. Edwin is also with us here. And I guess we have to be a little shorter on the questions afterwards because of the delay. But Edwin is going to answer them in a written form in the chat function. So Edwin will respond right during a pre-recorded talk. So please do ask your questions in a written form, and he's going to respond very, very quickly. Okay, to our video team, please blend over to the pre-recorded video.
Okay, welcome everybody. My name is Edwin, Delta Charlie 9 Oscar Echo. And today I would like to talk about a subject that is not so well known or not so commonly used in amateur radio, which is the usage of higher order Nyquist zones with direct sampling devices. I use STEMLab 16 from Red Pitaya as an example, but of course the principle applies to any other direct sampling system. I'm not alone. We work as a team. This is Markus, Delta Golf 8 Mike Golf, another Markus, Delta Lima 8 Golf Mike, Erwin, Delta Lima 1 Fox Yankee, and myself, of course. We work as a team since 6 years now on the subject of software-defined radio. It all started with our own development, basically, in 2014, something like that. But later on in 2015, STEMLab came up, Red Pitaya came up with STEMLab 14, and we found that the STEMLab device is much more flexible than our own developed hardware. And we started to use the STEMLab 14 as the basis for our further developments. It worked pretty well, but we were not completely satisfied because of the 1 megaohm input and output and all the analog components in front of the analog digital converter and of the DAC. And so we requested Red Pitaya to modify a STEMLab 14 for us and come up with a version which has direct access to both the ADC and the DAC. I think we presented the results at one of the software-defined radio academies in the past already. So our request to Red Pitaya was heard. They developed a new STEMLab with 16-bit analog digital converter and 14-bit DAC and direct access. So this device now has 50 ohm input and output and has much better performance than the former 14-bit version. And so this version is now the basis of all our further work. And one of the great benefits, and that's why I talk about the subject today, is that it has no anti-aliasing filters in it. So you have additional possibilities and additional functionality that cannot be accessed on STEMLab 14. Based on STEMLab 16, we have built a lot of hardware about it. So this is basically our work for the Nyquist Zone 1. So we built modules that like the pre-selector, the main board, the codec board. You can buy those and build your own radio transceiver for shortwave from 1.8 to 50 megahertz. It works pretty well, and if you want to have a pre-configured device from us, you can have it as well. So this work is considered more or less finished, and that's why we look into new opportunities and we go the next step. So why are we talking about the usage of higher order Nyquist zones here for TX and RX? Basically, we have a clock rate of 122.88 megahertz. And therefore the Nyquist Zone 1 covers 0 to 61.44 megahertz. However, any multiple of the clock rate creates additional Nyquist zones. And each of those Nyquist zones can be used. So when you switch on a basic frequency like 22.12 megahertz, then of course you also get in Nyquist Zone 2 122.88 megahertz plus 22.12 megahertz, which is exactly 145 megahertz. So this means the system is usable on 2 meters, for example. So the principle allows us to use multiple Nyquist zones and evaluate their performance for other use. So some frequencies can be accessed directly, like 4 meter and 2 meter. And in other cases, we need an IF frequency, and we would like to use a STEMLab 16 as IF processor for the higher frequencies. Our plan is to add 4 meter, 2 meter, 70 centimeter, 23 centimeter, 13 centimeter, and of course an access to S-Hale to our transceivers. And maybe if we have fun doing so and we are finished with all of those, we will build other bands as well. In an overview, it looks like this. You have Nyquist Zone 1, 0 to 61 megahertz here. The center frequency is 30.72 megahertz. You can assume a transverter bandwidth of 30.72 megahertz plus minus 10 megahertz. And this gives you in Nyquist Zone 2 92.16 megahertz plus minus 10. So you can see that the 4 meter band is seen here. In Nyquist Zone 3, it gives you 153.6 megahertz plus minus 10. The 2 meter band can be directly accessed here. And then the Zone 4 and Zone 5 is interesting because it gives you 215 megahertz and 276 megahertz. And we find those two frequencies attractive, and we are investigating them to use as RX and TX IF frequencies. So that's basically the idea. To give you a better overview, here you can see all the frequencies. This is Zone 1, the baseband which we currently use from 160 meter to 6 meter. Then in Zone 2, 4 meter is directly accessible. Then in Zone 3, 2 meter would be directly accessible. And then we have those two intermediate frequencies here, which we will use in our future projects. So doing this causes some challenges. The signal quality and the spurs and all the other clocks and any other unwanted Nyquist signals which come from mixing. And especially the clock represents a big challenge when we want to use those two frequencies. So one word for the challenge here is filtering. We need to build pretty good filters to be able to get all the unwanted signals out and just leave the wanted signal in. And this is true for both receiving and transmitting, but especially in the transmitting case, you don't want to transmit unwanted signals. Simulation shows that it takes a 7 to 9 pole filter structure, which causes a challenge. Of course, in a simulation it looks easy and it looks good, but in practice it's not so easy and not so good. So I have tried to build some 7 pole and some 9 pole filters first, and this led to pretty poor results. adjusting them was a nightmare, and it's not easy to build those filters. So I went back to another filter structure. I used a P filter structure, which is the structure we use in our preselector for shortwave currently very successfully for 11 bands. And I built a 5-section P structure for 215 megahertz. You see the result up here in the range from 1 megahertz to 1 gigahertz. The filter works pretty well. One problem was the coils. I tried to use SMD coils, but of course it doesn't work. The Q is very low of those coils, and of course it cannot be adjusted. So I built my own coils. Here you see an M3 nut, and here you see the coils, and here's the filter, and here's the filter structure that you see. So the result is those filters can be built. You can build them yourself. It's not rocket science, but it's just a lot of work, and it's fiddling around with the coils and the filter structure to get to a filter performance like you see above. So it's difficult to build something like this on a repeatable basis. And as we want to build more of those transceivers, we are trying to find other ways of filtering. There are basic two alternatives in our view. One is the usage of helical filters, and one is the usage of surface acoustic wave filters. Helical filters are available commercially from a company in Taiwan. A company is called Temwell, and they have very nice 5-pole filters for 215 megahertz and for 280 megahertz, and they are willing, or 290, I think, and they are willing to adjust those filters to 276 megahertz. So the filters would exactly do what we want. But there's a little disadvantage, which is cost. First of all, those filters are not very cheap. They are pretty expensive, something in the range of $30 to $50. And the second disadvantage is you have to buy a minimum of 200 or 300. So we are currently discussing with them if there's other alternatives, but it looks as if for cost reasons we cannot go this path. The other possibility is the usage of surface acoustic wave filters. They are difficult to find, but there are two companies, or at least we were able to identify two companies who make those filters. And you see one of those filters here and the other filter here. Vectron International is one of those companies. They are based in California, and they have some pretty good filters. And there's another company in China, which is Winsky, and they have some nice filters as well. Both are willing to provide us some filters. We need to see, first of all, what is the performance of those, and then, of course, what is the cost of those. It looks as if the curves are a little bit bumpy here, and we might have to use two filters all the time to be able to get to a clean signal. So filtering is a big subject, not easy to solve, but it can be done. And of course, we have done some measurements on the frequencies that we want to use. One frequency is 215 megahertz, and we would like to use 215 plus minus 10 megahertz. We might have to reduce this to 215 plus minus 5 megahertz because there are some spurs around the frequency which are difficult to get rid of. I cannot go into the details here, but the work is still going on to look into it a little bit in more detail. The MDS is pretty reasonable with minus 118 dBm at 500 hertz bandwidth. The maximum possible input which is accepted by the ADC is plus 1 dBm. So the maximum possible dynamic range is roughly 119 dB. On the TX side, the power output is minus 15 dBm. By the way, in zone 1, it's minus 1 dBm on the same frequency. And the IMD looks pretty good as well. It's minus 50 DBC, but the IMD is depending on the output level, so you have to be careful. You can get a higher output level here, but then IMD goes down pretty quick. I was not able up to now to find out why, because I don't think it's the DAC who does the IMD. I believe the output transformer, which is on the STEMLab, might have a little bit too small core. Anyway, you have to be careful when you build something like this about the power you are using. So the same on 276 megahertz. MDS is the same as with 215 megahertz, and the input range is also the same as with 215 megahertz. The output was about 3 dB lower, but otherwise it's exactly the same. Also here the IMD is depending on the output level, so you have to be careful. And when you build a transverter on this basis, you need to understand what the signal chain and the output levels look like. When you do some practical tests, and I did those practical tests with the simple filter I showed before, basically the unfiltered signal looks like this, lots of signals and spurs, and so without a filter the signal is not useful. You see here the 115 megahertz, the 153 megahertz, the 275 megahertz, and other unwanted signals. So they all need to be filtered out. I did it with the filter from page 10, and you see on the right side that even with this crude homemade filter, the output signal is pretty good. All the unwanted signals are gone. So it can be done with a simply homemade filter, but as I said, setting it up and adjusting it is pretty cumbersome. It's interesting to look a little bit closer and see what the IMD looks like. In this case, it was minus 52 dBc. And I have not shown 276 megahertz here because the result was exactly the same. It was minus 52 dBc on both the 215 megahertz and the 276 megahertz. A little bit of a problem, if you look very close, is the spurs around the carrier. There's one spur which is pretty high at minus 43 dBc. We need to find out if those spurs can be impacted by the code which is run in the FPGA or by any other measures. We don't know yet. We need to investigate and see if the spurs can be reduced. So this causes a little bit of a headache, which we need to look into. Based on this idea, we will build transverters for all sorts of frequencies, and I've put up an example here for 2.4 gigahertz and the Oscar 100 downlink. The design we do will be based on modern state-of-the-art semiconductors. The reason why I say this, or I point to it here, is because those semiconductors are very, very small, which means the new design will not be a homemade design anymore. Nothing that you can build in your own hobby shop. It needs to be done commercially. Also soldering and the picking and placing needs to be done by a commercial machine. But the semiconductors do have very good data, so it's attractive for us. So the mixer, for example, has an IP3 of 29 dB and covers a frequency range of 10 megahertz to 6 gigahertz. And there are also nice oscillators available, the HMC H30, which goes to 25 megahertz to 3 gigahertz, or the H33, which goes up to 6 gigahertz. And of course, we will plan for a 10 megahertz reference internally or externally to be put in, so you can link your transverter to the GPS. This design principle will be used for any VHF, UHF, and SHF bands, except those where we use the direct sampling principle. And the example you see on the right is for Oscar 100. We will build a transverter which is capable of transmitting on 13 centimeter, but in the complete band, so you can use it for normal 13 centimeter work as well. And on the RX side, we will use the RX1 for 13 centimeter, and the RX2 will be used for 744 megahertz. So this is useful for the downlink from Oscar 100. You can use a standard LNB then to receive Oscar 100, as many amateurs already do. So this will be the transceiver design. You can look into the details if you like. I don't want to go into them here because I think it takes too much time. And then for those of you who want to experiment a little bit, I've put up the data for a 2-meter filter, which can be relatively easily built. This filter uses T50-12 cores and has 6 turns on each of the filter coils, and it uses standard NP0 capacitors here. So it can easily be built and tweaked by tweaking the coils. And the result that you will get out of this filter can be seen here. It is a pretty narrow filter, and it's good enough to filter the output of STEMLab 16. So you get a pretty clean signal out of it. And you also get a very good IMD behind of it. So the not negatively impacting the IMD of the output signal. The signal will still be at minus 55 dBc. So this is for the home brewer, and some of you who have fun to build something themselves. And finally, here is a little overview of what we plan. So based on the principle described before, we will build transverters for all the higher amateur bands. For 4-meter and 2-meter, we will eventually go the direct path with direct sampling, and we will add a power amplifier in the 20 to 50 watt range. The exact numbers are not clear yet because this is under development, and we will see what can be more or less easily built. Then we plan transverters for 70 centimeter and for 23 centimeter. And of course, for 13 centimeter and including the SAL part, which I described before. For the 13 centimeter transverter, we will probably plan for 2 power amplifiers, one with 20 watt for standard voice and data transfer, and maybe a 100 watt power amplifier for digital video broadcasting, so that you need, or you get a little bit more power for your broadband transmissions. So, and that's basically our plans, and that's what we do over the next, let's say, 6 months to 12 months. I don't know yet what will be finished when, but if you want to follow us, there's a page on Facebook that you can follow, and of course you can see our shop where we will put the latest stuff in up here. So it's easy to see what we do. And here I'm at the end. If there are any questions, I think we can discuss the questions now. Thank you.
Okay, so fantastic. Thank you very much, Edwin, for this very interesting contribution. We've just had a little conversation in through the back door, through the one of our studio rooms. Well, we had a problem in the network in the beginning. Obviously, the LTE tower failed to operate, which was not our fault, but the LTE connection was gone, and it's not coming back. And so we have kind of this problem. In order to save time and to catch up a little, first of all, I would like to thank Edwin very, very much for this contribution. It was an interesting contribution. Thank you very much, Edwin. We've talked just before that Edwin is going to respond to the questions in a written form in the chat, and he has already done so, and he's going to continue to do so. And if there are any questions, you can of course always contact him directly. So